It's a pleasure to be here. It's my first time in India, first time in Bangalore. It's a wonderful place to visit. So I'm going to tell you about today about our work on atomically thin sodium-3 bismuth, which we're calling a platform for topological electronics. And I'll explain what that means. So I'm at Monash University. This work is quite collaborative. We work closely with Shafiq Adams' theory group at National University of Singapore, and also Shengyuan Yang's theory group at Singapore University of Technology and Design. And there are experiments done at 2 different synchrotrons, and also we work with Dimi Kulser, theorist at UNSW. Okay, so this work is part of a center of excellence that I'm directing in Australia called FLEET, Future Low Energy Electronics Technologies. The goal of this center is to come up with transistors that can switch at lower voltage or lower energy, so classical transistors, not quantum, not qubits. And the reason for that is that computation now uses 8% of the electricity globally, and that's a number that's actually going up and will go up faster when Moore's law ends and we're not able to make conventional transistors better. So there are a few approaches we're taking. We're particularly interested, just because we thought it was a good area to look, in mechanisms for electronic conduction without dissipation at room temperature due to some new physical phenomena. One is topological edge modes of 2D topological insulators. Another is exciton condensates, especially indirect exciton condensates. And then the third is non-equilibrium or using time-dependent fields to induce either topology or superfluidity in a material. And then we want sensitive switching, either based on this quantum phase transition from trivial to topological insulator or this collective electron phenomena of exciton condensation. So the one I'm going to talk about today are the topological edge modes in this quantum phase transition. And so the idea is that we have this vision of a topological transistor, which is a 3-terminal device where a gate controls current from source to drain. And what's going on under the hood is that this gate will somehow transform this material from conventional to topological. And then when it's topological, it'll have some edge modes, some ballistic one-dimensional conductors that will carry current from source to drain. Okay, so outline for the rest of the talk, I'm going to talk about Dirac materials. I'll start with graphene as a prototypical example and talk about the connection of these Dirac materials to topological insulators. And then I'll talk about this sodium-3 bismuth, which in 3D in the bulk is a 3D topological Dirac semimetal. And then when it's thinned down to atomically thin, just a few layers, it is a 2-dimensional topological insulator. It's in the quantum spin Hall phase. And I'll talk about our work. We've done a lot of work on this system, but I won't really have time to talk about it. So I'll just focus on the 2D topological insulator, particularly electric field, using electric field to tune through this topological phase transition and convert it from topological to trivial. And also some recent transport experiments where we can see edge state conduction over millimeter distances, and that edge state has a novel giant negative magnetoresistance. Okay, so I said I'd start with graphene. Graphene is a honeycomb lattice of carbon atoms. The single particle band structure of graphene was worked out quite some time ago, in 1947, within tight binding. And the graphene has 2 bands, a full band from the 2 pi orbitals of the unit cell, and an empty band. But it would be an insulator, but these bands touch at these special points, and they're preserved by the symmetry of the fact that the 2 atoms in the unit cell are identical. And so the low energy graphene looks like this. It has this Dirac point. It has a Hamiltonian, which is, has this sigma dot p form, so it's often compared to a massless Dirac equation. So energy is linear in momentum, et cetera, et cetera. So early on in graphene days, Charlie Kane and Jean Malie thought about what are the possible perturbations to graphene that might arise spontaneously or might be there anyway, and that might alter the ultimate ground state away from this Dirac point. And so this is the Hamiltonian now with including both valleys. And so they considered this staggered sublattice potential, where you can imagine that perhaps there's some spontaneous charge order that produces a different potential on the two atoms in the unit cell. That opens a gap in graphene. So this is a calculation on a finite ribbon of graphene. And they considered spin-orbit coupling. For example, if you have spin up and spin down, you may hop in different directions, or second nearest neighbor hopping. And that also opens a gap at the Dirac point. But now we understand that these two gap systems are different. This is a conventional insulator, and this is a topological insulator. And then you could see that in this calculation on a finite width ribbon, that there are extra states here that span the gap, and those have to be there. So that was what's going on. These extra states live at the boundaries, they live at the edges, and they carry spin, opposite spins in opposite directions on each edge. So graphene, this is actually thought to be the ultimate ground, the actual ground state of graphene. There is spin orbit coupling in carbon, although it's very, very small. But the spin orbit coupling is quite small in graphene, so it's difficult to detect experimentally. But if you use a strong spin orbit coupled material like mercury telluride, you can create this 2D system. The Hamiltonian is a bit different here, but you could create a quantum spin Hall phase where you have a gap and you have edge modes within the gap. And that is seen experimentally, that if you tune the Fermi energy into the gap, the resistance doesn't diverge. It saturates at this conductivity of 2e squared on h due to these two perfectly conducting edge modes in the system. Okay. So there's two kind of lessons here. We can realize these topological Dirac semimetals that have this Dirac point and this unusual Hamiltonian, and they lie at the boundary between conventional insulator and topological insulator, and so perturbations can push them one way or another. This is graphene's the 2D example, so we can ask, can this happen in 3 dimensions? And it can. Typically, so if you imagine tuning along some axis, such as the mass term in your Hamiltonian, that it would invert the band structure from normal to topological, there was a critical point at which you would have Dirac points in your material. This happens, for example, in the bismuth antimony alloy series as a function of antimony concentration. You can tune through this point. This does require fine tuning. And these points can interact, and then so they can, in principle, become gapped. And so this is it's not the best way to do it. But it turns out if you add an additional symmetry, so in addition to the time reversal and inversion symmetry, if you have some rotational symmetry in your system, you can actually preserve this topological Dirac semimetal over a range of parameter space. And so you can have these Dirac cones in 3D. The first such material where this was proposed theoretically is in the alkali metal 3 bismuth materials, sodium 3 bismuth, potassium 3 bismuth, and observed experimentally soon thereafter. So these materials have these hexagons of sodium bismuth, and then there are extra sodium atoms above and below each hexagon. So they're it's a somewhat layered structure. The Dirac points in a 3D Dirac semimetal don't lie necessarily at high symmetry points. They lie, in this case, offset from the gamma point along the z-axis in the material. And there are just two Dirac points in this particular material. So you have, again, this linear energy momentum relationship. It's anisotropic, so the velocity is lower along the z-axis. Okay, so again, we want, our goal is to get to something like this, where we can use an electric field to tune the topology in a material. You can see that there are possibilities here, even in Charlie Kane and Jean Millie's first paper. They have this phase diagram where this is the quantum spin Hall phase, this is a normal insulator. Graphene lies at this black boundary where we have a topological Dirac semimetal, and these are these different potentials. In fact, they considered a Rashba potential and this sublattice, staggered sublattice potential. And in fact, they're both tunable by electric fields. So Rashba can be tuned by an electric field, and the sublattice asymmetry could be tuned by an electric field if you had a staggered sublattice. For example, this is sort of one phase of silicene. Bismuthine also adopts this phase where you have these atoms displaced out of plane, and so a vertical electric field will cause a different potential in the two atoms. And so one could imagine tuning around in this phase diagram with electric field. And that's been proposed in quite a few materials in various ways. So there are actually different mechanisms here. Some of them were not considered in Kane and Mali's paper. So for example, topological crystalline insulators, if you break inversion symmetry, you will open a gap on the edge modes. In these cases, in silicene, you have this staggered sublattice that was talked about in this paper. In the 1T prime TMDs, like molybdenum ditelluride, tungsten ditelluride, it was actually in the first paper that proposed that those materials were topological by Liang Fu's group. They also found that a Stark effect would due to electric field, would rearrange the bands and cause this transition. And also in sodium-3 bismuth and cadmium-3 arsenic-2. So in essentially every topological material you can think of, there's probably some electric field effect that will actually rearrange the bands. So sodium-3 bismuth is the one we're interested in. This I'm showing now some DFT results on monolayer and bilayer sodium-3 bismuth. If you make it very thin, these two materials are actually topological insulators with very large band gaps. Predicted band gaps on order 300 millivolts. And you can see edge states if you do the projection of the band structure onto the edge in monolayer and bilayer. With Shengyuan Yang's group, we did DFT as a function of electric field, and you can see that this band gap actually closes to zero and reopens. And at this point, at zero electric field, it's topological. And at this high electric field, it actually becomes conventional. And you can see if in the orbital projected band structure, you can see that that here you have this inverted, P levels above the S levels, and now you've uninverted that. And this is happening again because of a Stark effect, that there's some mixing of these nearby bands with other bands in the band structure. Okay, so that's nice. It looks like a nice system to work on this electric field effect. I'll talk a little bit about working with thick films of this material. The challenge with this material, sodium-3 bismuth, is that it's highly reactive in air. So we do all the experiments in ultra-high vacuum. We have this nifty setup where we can, it's hard to really see what's going on. There's an MBE chamber here. There's a dewar with an STM at the bottom of it there. And we can grow the material, we can move it into the cryostat, and we can do scanning tunneling microscopy, and we can do transport experiments. Our devices look like this, where they're wired up to some electrodes, and we can connect to those wires. We can also put the STM tip right down in the middle of the device and do STM. Okay, so we can grow nice films. This is STM of a thick film on silicon 111. You can see terraces that are over a couple hundred nanometers. You can resolve the sodium atoms on the surface. This is a missing sodium atom vacancy, which we do see. We can grow them also on alumina, which is insulating, so we can do transport measurements. We have looked at electron hole puddling, which is sort of a ubiquitous phenomenon in Dirac materials. If you're familiar with graphene, it turns out that sodium-3 bismuth is quite smooth. It's as smooth as graphene on hexagonal boron nitride. The potential fluctuations are very small, and largely that's due to 3D screening. And we've been able to optimize the mobility. We can get mobilities of about 7,000 centimeters squared per volt second at low temperature, and carrier densities down to about 4 times 10 to the 12 in 2D, or 2 times 10 to the 18 in 3D. And so that's pretty good. This is comparable to the best really low-doped crystals. High-doped crystals may have higher mobility. Okay, and there's other work that we've done that I won't talk about. So really, I want to get to what happens when you go to 2D. I think that's maybe more interesting. So we can thin this material down. This is a film deposited on silicon, so it's nominally 1 layer thick. And what we see is regions of bare silicon in red. This is, again, scanning tunneling microscopy. We see monolayer regions in purple, and we see the start of bilayer regions in this sort of light gray purple color. So we can grow a film that's mostly monolayer. It has some bilayer regions. If we do scanning tunneling spectroscopy on this film, now here we're measuring again, this is the differential conductance versus bias, which is local density of states versus the energy. And we see a large gap. So we see a gap of around 300 millivolts. I think it's plotted here. So our experimental gaps for monolayer and bilayer are about 360 and 300 millivolts. It's a little bit bigger than the DFT predictions, which are in red. When we include a sodium vacancy, the gap is a little bit bigger in the bilayer. And so that I think it's in reasonable agreement with DFT. Typically, DFT underestimates band gaps. Angle resolved photoemission spectroscopy also shows that this material is an insulator. So ARPES measures directly the binding energy versus momentum, and we see a filled valence band and no states at the Fermi energy. So this is indeed an insulating material. The spectrum's a little bit complicated, but we can take the second derivative of the spectrum, and it kind of highlights the band features. So there's essentially 3 sets of bands. There's one here, there's another one here, another one here. They all have their maxima at gamma. The DFT for monolayer and bilayer is shown overlaid. And the DFT also shows 3 sets of bands in the DFT calculations, so it agrees reasonably with experiment. There's some features here that are probably due to both monolayer and bilayer. The fact that there's a dispersing band and a flat band here is a bilayer characteristic, and this little extra feature here seems to be a monolayer characteristic. So and that's fine. I mean, they're both in this sample, but it's all insulating. It's all gapped. We can verify that this is a topological insulator, not just an insulator, by doing scanning tunneling spectroscopy right up to the edge of a terrace. And so in the bulk, in the black, we see a gap. We see low density of states. This is on a log scale. We see low density of states in this gapped region, and on the edge, we see extra density of states within the gap. Yeah? It's noisy, and I'm sorry, but it is on a log scale, and it's also just turned out it's a little bit noisier in this measurement. Yeah, I mean... it's not that going to make the gap. No, this is essentially the same sample that I showed before. It's just that it happened to be noisier in this measurement when we tried to look at the edge. It's a little bit tricky to look at the edge. There is a feature that's consistent. There is a dip here at 0, and that's real. And in fact, you can see that in the edge, there's this pronounced dip at 0, and that's thought to be due to basically a pseudo gap due to Luttinger liquid phenomena in the 1D edge. And so that's been seen, for example, in bismuthine. So that feature is real, but I'm not sure what the other features are. It may be real, or they may be noise. If we average over this gapped region, so the spectroscopy energy axis is vertical and distance from the edge is horizontal. If we average over this gap region, the density of states here, we get this curve. It falls off roughly exponentially into the bulk over a distance of a couple of nanometers. So this is really some kind of electronic state at the edge that's falling off into the bulk. It's not some chemical state that only lives on the atoms that are right on the edge. And so that seems reasonable for a topological edge mode. So this is bilayer. So bilayer sodium 3 bismuth certainly looks like a 2D topological insulator, and that again agrees with DFT. And I would think the ARPES agreement and band structure also tells us, I think we can be fairly confident this is a topological insulator. So we can use electric field. We've done this a couple of ways. I'm going to just show one. So we use a scanning tunneling microscopy tip, which has a very different work function than the sample. So it's about 1.2 eV higher work function than the sodium-3 bismuth, which has a very low work function. And so there's a built-in electric field, even at zero bias, between the tip and sample. And so as we vary distance between tip and sample, we can change electric field. And so this is what this looks like. As we increase the tunnel current or make the distance smaller between tip and sample, first we see this large gap, about 300 millivolts. This gap gets smaller and smaller as we bring the tip closer. Eventually it closes down to zero, and there really is no evidence of a gap here. And then if we keep bringing the tip closer, the gap actually reopens, which is quite surprising that you can close it, metallize it, and reopen it. So, well, we think this, this is our picture of what the tip is doing. At this tip, the electric field can take these knots, these topological knots, close them down to zero, and reopen them, and they're untied. So that's pretty cool. We can make a phase diagram of bandgap versus electric field. It turns out we looked at monolayer and bilayer. This got a little bit messed up. They both actually have a bandgap that closes to zero at a very similar electric field and then is reopened just slightly. This is about as far as we can push the experiment. This is not a terribly high electric field. 1 volt per nanometer can be actually realized in a field effect device. Okay, so this is all published last year in Nature. 2 years ago now in Nature. I'll tell you about some more recent stuff now looking at transport experiments in the same material. So to do transport experiments, we need to grow on an insulator. So we grow on this sapphire. I won't go into the details, especially for this audience, but again, we've got a combination of monolayer and bilayer. It's not quite as pretty, but this is a histogram of the heights, and this is monolayer, this is bilayer. And we expect, again, that they're both topological. So this whole system, even though it's got a variation in layer number, it's all a topological insulator. The devices, again, look like this. We can actually grow this Hall bar onto pre-existing electrodes. This is actually a device on silicon dioxide on silicon, but they look similar to this on sapphire. It's just harder to see the film. Okay, so the first thing that we can do, the as-grown films are slightly doped. So then we're measuring the 2D bulk of the film, which is metallic, so it's slightly n-doped. I'm showing actually 4 different samples here. These are 4 as-grown samples, and they have different doping levels. So this is carrier density, and they're around 10 to the 11. So the doping is low, but they are doped. And I'm showing magnetoconductance. So this is the change in conductance versus a small magnetic field. And we see these sort of cusp-like features. And this immediately makes us think about weak localization effects. Okay. And so weak localization results from some scattering and some quantum interference around some path around multiple scattering sites. The path and its time reverse partner necessarily constructively interfere and lead to enhanced backscattering. If you can scramble that with a magnetic field, and so generally what you find is that the localization happens at zero field, and then you reach the classical conductance at very high field, and so there's this characteristic positive magnetoconductance due to weak localization. So Dirac materials are different. Dirac materials, because we have this spin momentum locking, we have this pi phase shift that we get when we go all the way around the Fermi surface. And so there we have destructive interference of backscattering. Backscattering is forbidden. And so we have enhanced conductivity at zero field. And so we have a negative magnetoconductance due to anti-localization. The generic 2D case where we have some spin orbit coupling, but not perfect spin momentum locking would be given by this HLN formula. It's rather complicated, but it has an additional parameter, which is this spin orbit length, which would be finite. I didn't show you this, but we've measured thick three-dimensional sodium-3 bismuth. That should be a topological Dirac semimetal. We get perfect weak anti-localization. The data here are in circles, and there are fits that are, you can't tell the difference between the data, but they're in there. There's solid lines, and so it looks very nicely weak anti-localized. So perfect spin momentum locking, as near as we can tell, in this 3D Dirac semimetal. When we go to 2D, you can tell already that there's some problem. This is non-monotonic in magnetic field. The conductance goes down and then it goes up. And so something is going on. So we can fit to this full HLN formula. We extract a finite spin orbit length. The spin orbit length here is decreasing, going towards more perfect spin orbit coupling as we go to larger density. And then there's a phase coherence length. And they roughly cross at this lowest density. So what's going on? We think at low doping, essentially, we have poor spin momentum locking. We're near the band edge here. So we've got long spin orbit length, and we tend towards weak localization. As we go to high doping, we have this short spin orbit length. It's good spin momentum locking, and that's what you expect. Now you're up on the Dirac cone, you don't feel the gap as much, and so you tend towards weak anti-localization. That's sort of a qualitative picture, but this, yeah.
Short LSO means weak spin orbit?
Sorry, long LSO means weak spin orbit. It means that the electron has to travel very far before it precesses. So if the spin orbit length goes to 0, that means that the spin and momentum are locked, right? I believe that's correct. Yes.
Yeah. Sorry, yeah. So the slight increase at large field, could that be electron scattering processes? Which is there any knowledge about that?
It could be. I'm not gonna. I don't know. I have to think about it. It's where I should think about that. Yeah. We're into question time.
Follow up on the same question.
Yeah.
What's the cycle of value for half the
Yeah. So the fits are actually. I think we fit only out to where the magnetic length is equal to the elastic length, right? So I think that's your question. Are we in the low field regime? Yeah. So the low field regime is actually represented by these fits. It's longer here, but it's actually quite a small portion of the fit at high density. Okay. So anyway, I don't want to make too much of this. I think the difference here, I would say, is consistent. The fact that we see weak localization at all, I think, is consistent with the fact that there is some hybridization of the Dirac cones, and that's what we expect when we open a gap. So we don't expect a system that has perfect weak anti-localization anymore. And I think that's the only real point I'm trying to make here. Okay, so maybe more interesting is to take this Fermi energy and put it in the gap, where we expect that we'd only have metallic edges and an insulating bulk. And we can do that with this molecule F4TCNQ. We can remove some carriers. We can dope into the gap. And when we do that, I'm going to show you two measurements. We're going to measure resistance in the usual way with a Hall bar. We run current down the middle. We measure voltage over here. And then we're going to do a non-local measurement where we run current around one corner and we measure voltage on another side over here. And we'll do that as a function of this F4TCNQ doping. So as we're trying to move the Fermi energy into the gap. So why do that? If we have a uniform conductor, then if we do this non-local measurement, we run current over here, we get almost no voltage here. In fact, for the geometry that we have, we should get 10 to the minus 3 for this non-local voltage compared to the local voltage. But if we have edge transport, then effectively the current runs all the way around. And so even if we run current over here, some of the current will go all the way around the sample and we'll get some voltage over here. And these are roughly comparable, so we should get something closer to 1. So they're separated by 3 orders of magnitude, so we can really tell the difference between edge transport and bulk transport. So here's the measurement. Again, we measure both of these. We take the ratio, and here's the ratio as a function of coverage of this molecule. It starts out down here around 10 to the minus 3, as we expect, and it goes up, and it plateaus somewhere around 1. And so an interesting thing happens. Okay, so the resistance here in this region is around 300 kiloohms per micron. It's not quantized. But it implies a mean free path around 100 nanometers, and that's similar to what's seen in, say, tungsten ditelluride. We also see this very nonlinear voltage as a function of current, and we interpret that as essentially at low current and voltage, we have this edge transport, so we get this big non-local signal. As we increase the current starts to flow through the bulk, and our non-local signal stops increasing because now the current's being shorted out by the bulk. And so we get this very sharp nonlinearity. And this scale here is about the size of the gap, and so maybe that makes sense. Okay, this is the last bit. So the edge is resistive, but I said that if we have preserved time reversal symmetry, this 2dTi should have a perfect conducting edge. We should get 2e squared over h, if we have two edges conducting. But experiments show that the conductance is much less than this in all TIs, if they're large enough, and there's little temperature dependence. And so that seems to be a mystery. One possibility is that this resistance comes about because you have local moments in your system, and they, so you have some exchange scattering with local moments, and if the temperature is greater than the Kondo temperature, it'll be roughly temperature independent. Okay, so the picture is that your edge electron comes along and it flips its spin with a local moment and it backscatters.
Then why do you have no local?
Because it's transport along the edge, right? I mean, it just says that the edges are resistive. They're conductors, but they're resistive conductors. They have a mean free path that's finite, that's all. Okay, and so there's an interesting effect due to that. One is that if we measure resistance as a function of magnetic field, this is this weak anti-localization that we see for the bulk. When it's in the edge regime, the edge conduction regime, you see that the magnetoresistance now is very large and negative. So we can compare to a theory for exchange scattering. So this was actually worked out in the 60s. It was worked out with a slight mistake in the calculation in 1963, and then that was corrected in 1968. If we just adapt that theory, we can fit our data. There's a single fit parameter. The only thing that's in here is the G factor. Essentially what we're doing is we're Zeeman splitting these local moments. Backscattering becomes inelastic, and so it's suppressed by magnetic field. The G factor is very large, but the G factor in sodium-3 bismuth is also large, and so we think that basically these local moments are just little puddles of electrons in this sodium-3 bismuth, and they have a big G factor. The resistance is suppressed more than 80%, and that's important because if we have exchange scattering in a non-helical metal, we can only suppress the resistance 2/3 because we can always still have scattering that preserves the spin. So the theory includes only spin flip scattering and fits the data quite well. And so I think the fact that this fits well is a smoking gun of the fact that these edges are not only controlled, not only is the resistance all spin flip scattering, but it's chiral spin flip scattering. Yeah.
By the time the largest contest,
Yeah.
what's the resistance?
Well, so the mean free path's about 500 nanometers, so that the resistance is h over e squared for 500 nanometers. But we have a millimeter, so the resistance is 1,000 h over e squared.
And it's still length dependent?
I don't know. Different lengths of the sample actually have resistances that seem to be different, and it seems to be that the sample's not completely homogeneous, which is not surprising that we grew this thing over a millimeter and it's only a nanometer thick. So I can't say that yet. Okay. All right, so that's all I wanted to say. I think this few layer sodium-3 bismuth is a nice platform for topological electronics. We can grow it on silicon and sapphire. It's got a huge gap, 300 millivolts. It's much larger than room temperature. We see chiral edge transport over millimeter distances. And it has this nice electric field tuned topological to trivial transition, which we've already demonstrated. And so this is the kind of material that you could use for a room temperature topological transistor. And I'll thank the people, again, that did this work. And if you're interested, the references are here. And thanks for listening.
Questions?
What is a topological transistor?
So the topological transistor uses electric field to turn a material from conventional insulator, which is insulating, to topological insulator, which has edge modes which conduct. So it's an electric field device that goes, it's a conventional transistor, but it uses a topology, yeah. It's not a quantum transistor or a quantum qubit or anything like that, yeah.
Still have a resistance.
Edge modes still have a resistance, and it turns out that doesn't matter. What matters is whether it operates at lower voltage. That's a very complex question. In principle, though, the fact that you've got these different mechanisms to use to invert the bands means that it's possible to have a low subthreshold swing, to have a low voltage switching, but whether that's really a huge advance or just a factor of 1.5 or 2, that's what we're trying to work out right now.
Well, I don't know, I'm sorry, just because it's a follow-up. I don't know whether you can say edge modes will have finite resistance. Depends upon how many probe measurements you're doing. Probably as a 4-probe measurement, you will not get resistance.
So our edge modes seem to be resistive. I mean, I'll admit that. But they have 100 nanometer mean free paths, and ultimately, if you want to make a transistor, you want to make it 3 nanometers. And everything is ballistic at 3 nanometers. It doesn't matter. So it's not that the edge modes are ballistic. It's more that there's a new mechanism to turn on and off conduction. In this case, it's a non-interacting single particle mechanism, but it is different than raising a barrier in a semiconductor.
So if I understand correctly, there's some you want to dynamically go from a trivial to a topological phase, is that right?
Well,
At some point,
yeah, we want to turn a knob. I mean,
Yeah.
it doesn't have to be fast, but we
Yeah,
at least
so I
want it to be
guess
fast.
that was exactly my question, because if you're going through the quantum critical point, you'll have the relaxational times really diverging. So I imagine that even if you go slow enough, so 2 things. One, just generically, you could have a lot of quasi-particle excitation. And then specific to this, there may be some very interesting dynamics in the way the edge modes themselves form. So
Yeah.
I'm just wondering.
It's a really interesting question. We would like to do those experiments where we use a time-dependent electric field on a material like this that has a very strong effect like this big Stark effect, and actually look at that dynamics. We haven't done that. It's interesting. I think it's unknown what will happen.
Hello. Hi. So does the magnetic scattering show up in resistance versus temperature also? And in terms of some sort of condo-like behavior, A, and B is in how many, so the STM is done along the STS is done along the voids, right? In the sodium-3 bismuth.
Yeah.
So in how many, I mean, just what percentage of voids do you actually see edge modes?
We see on all of them, but all of them is like 2 or 3. I can't remember how many we looked at. But we haven't looked at a lot. So I don't have good statistics on that, but at least it's there. In terms of temperature-dependent resistance, we would really like to do that. It's an experiment we're trying to do right now. We have very limited capabilities in the cryostat that's in UHV. It's, the system was designed to do STM and not, variable temperature transport measurements. And so we've only been able to do measurements at 1 temperature and up to 1 Tesla. We'd like to do it at different temperatures. The theory is that we're in the regime that we're above the Kondo temperature. Eventually you could freeze out these moments by going to low enough temperature, they'll form singlets and the system will become perfectly conducting again. But the theory is that there's always going to be some very weakly coupled moments, and so you've always got those around, and those are the ones that are giving you this temperature-independent scattering.
Very experimental question. You used F4TCNQ for doping.
Yeah.
That's somewhat unconventional for an inorganic system like this.
It's our whole dopant of choice, and this thing has such a low work function that probably anything that you put on it would whole dope it, but at least it's a molecular dopant, so it probably is weakly interacting, right? It's less likely to form some covalent bond and some strong defect or something. Okay. Yeah.
So I've heard from my experimental friends who work on the bulk material, they're kind of scared of using the sodium-3 bismuth because it's exposed to air, it does bad things. I don't know, is that a problem for the film or?
Look, in terms of using this stuff to really make electronics, I think what I would say is, what we've shown is that it's possible to make a material that has a really large topological gap and conventional gap, and you can switch between them, but this is probably not the material that we want. So I think now that we've done this, we're thinking very hard about how you design these materials and also how you want to do the switching. I mean, this is one particular switching mechanism, but it's not the only one. As I mentioned, you could use, material, you could use Rashba, you could use a topological crystalline insulator and just break inversion, symmetry. I mean, there are other ways to do this. And so I don't know which is the best way. Yeah.
So in case of the 3D limit, the change in the conductance that you have observed, that was for up to 4 Tesla, 5 Tesla regime you have went. But in the case of 2D limit, why that changes occurred only in the low field regime?
You're very observant. I showed some nice data here out to higher field, and this is tantalizing because we actually were able to take this sample. This is the kind of thing that we want to do with our 2D sample. So this is a film that we grew in this UHV chamber. We capped it. In this case, we capped it with magnesium difluoride. We took it out of the UHV chamber, put it in a cryostat, and it survived. It's actually much more disordered. The mobility is lower. It's only about 100 in this film, but it still shows perfect weak anti-localization. It means that you can still make this thing kind of disordered, and this Dirac cone behavior is still there, which I think that's good. So we'd like to get the capping to work a little bit better so we don't make the films too disordered, but at least it's promising that we are able to do that transfer to a cryostat. Yeah.
Okay, let's thank the speaker. If there are more questions, you can talk to the speaker during the break. And we'll assemble again at 3:45 for the next talk.